In the heart of Seattle's Boeing plant in 1943, the rhythmic sound of pneumatic hammers echoed through vast aluminum halls. Rivets flew like silver sparks, smoke hung in the air, and beneath the towering half-assembled fuselage of a B-17 flying fortress, a young riveter named Eleanor Watkins adjusted her goggles and stared at the massive wing structure before her. She was 24, one of thousands of women who had stepped into the factories to replace the men who'd gone to war. Every line, every joint, every sound was familiar, but something about today felt different. The war had pushed everyone to their limits. Every day, engineers demanded more planes, faster assembly, and fewer mistakes. But the wings, those massive, intricate assemblies of aluminum ribs and spars, remained a bottleneck. It took nearly 20 hours just to align and secure them properly, and if a single rivet line was off, the entire process had to be redone. Each hour lost meant another bomber delayed from reaching Europe, another crew waiting for the machine that could carry them home alive. That morning, Eleanor noticed a subtle flaw in the process. The assembly teams always began riveting from the outer edge inward, following the manuals and the engineer's sequence. But as the panels heated, cooled, and flexed, they misaligned just enough to require adjustments that ate hours. It was the way it had always been done, until she decided to try something different. During a lunch break, when the floor was quieter, she reversed the order. She began from the central spars outward, allowing the metal to breathe evenly, locking the core first before the edges. It wasn't in any manual, and if her supervisor saw it, she'd likely be written up for breaking protocol. But as the wing settled into place, the panels aligned perfectly. There was no need for rework, no need for adjustments. What normally took 6 men half a day had taken her team less than 2 hours. She didn't think much of it, just a practical adjustment born from intuition and fatigue. Yet that small act, unnoticed by most, would soon ripple across an entire industry. By mid-1943, America's industrial might had reached an unprecedented scale. From the shipyards of Richmond to the aircraft plants of Wichita, the nation had become the arsenal of democracy. Yet even with its seemingly limitless production power, the air war over Europe devoured bombers faster than they could be built. Each B-17 lost in combat represented thousands of parts, hundreds of workers, and hundreds of thousands of rivets, all assembled under tight deadlines. At Boeing's Seattle plant, the Watkins Pattern, as her colleagues quietly began to call it, started spreading. At first, it was just a rumor, a different way to rivet that somehow cut hours without compromising strength. Then the inspectors began to notice. The wings built using Eleanor's reversed pattern showed cleaner alignment and fewer structural deviations under stress. When engineers finally traced the change back to her team, there was disbelief. This wasn't a lab-tested innovation, nor the result of an engineer's redesign. It was the idea of a line worker who simply understood how metal behaved under pressure. Boeing's chief production engineer, Robert Minshall, personally examined the data. His report was brief and definitive. It works, and it works better than expected. The War Production Board soon took notice, and the method was codified under the name Revised Wing Assembly Pattern No. 7A. No credit was attached. In the official records, it was simply a process improvement, but among the workers, everyone knew. The results were undeniable. Assembly time for a single B-17 wing dropped from 20 hours to just 2. Labor hours per plane fell dramatically, allowing Boeing and its subcontractors to meet the impossible demands of the U.S. Army Air Forces. Where production had once strained to keep up, now it surged ahead. The B-17s rolled out of the factory gates in steady rhythm, machines of war born not from new blueprints, but from one riveter's quiet defiance. Her idea didn't just change efficiency, it changed the culture. For years, innovation had come top-down, from engineers to workers. Eleanor's pattern proved that understanding could flow the other way too. Newspapers occasionally hinted at factory ingenuity and worker-driven breakthroughs, though her name never appeared. She didn't mind. The recognition that mattered was in the hum of the factory, the knowledge that her method was now part of the daily rhythm keeping airmen alive. Across the ocean, those same bombers she helped build were flying deeper into enemy territory than ever before. Over Schweinfurt, over Regensburg, over Berlin, waves of B-17s thundered across the skies, their wings assembled faster, straighter, stronger. The men inside them had no idea whose hands had shaped their planes, but each one carried the unseen fingerprints of thousands of workers like Eleanor, people who would never set foot on a battlefield, yet fought their own war with precision and persistence. By 1944, B-17 production had peaked, and America's war industry was shifting toward the next giant, the B-29 Superfortress. It was larger, heavier, more complex, with over 100,000 parts. Once again, the engineers worried about production time. But this time they didn't underestimate the insight of their workers. Eleanor's reverse sequence became part of the initial design instructions, a quiet acknowledgement that the front lines of innovation weren't always behind desks. Her contribution remained buried in technical memos and forgotten manuals, but its legacy outlived the war. The Watkins Pattern became a foundation of modern aircraft assembly logic, influencing how wings, fuselages, and even spacecraft structures were aligned in decades to come. In the quiet years after the war, when the factories returned to peace, Eleanor left Boeing content to fade back into anonymity. She never sought fame or reward, but each time she heard the distant echo of an aircraft engine overhead, she knew, somewhere, in the seamless strength of its frame, her hands had left a mark, because in the vast, mechanical war of machines and men, sometimes victory was shaped not by generals or scientists, but by a single worker who saw what everyone else missed and had the courage to try something impossible. When the first B-17s were built in the late 1930s, they were practically handcrafted. Skilled teams of engineers and machinists spent over 30,000 labor hours building a single plane. As the war expanded, those numbers became impossible. The Army Air Forces needed thousands, not hundreds, of bombers. Factories in Seattle, Wichita, and Long Beach ran day and night. But bottlenecks kept forming. One of the worst was at the wing assembly stations. The B-17's wings were massive, each over 100 feet in span and composed of thousands of rivets, bolts, and overlapping aluminum panels. Building one wing took an average of 20 hours of combined labor across multiple teams. If anything slowed, a misaligned panel, a missing tool, an overworked riveter, the entire line backed up. Engineers redesigned jigs and fixtures. Managers revised blueprints, but the problem persisted. It wasn't technology holding them back. It was human rhythm, the invisible patterns of work that determined how fast a crew could move in perfect sync. At Boeing's Plant 2 in Seattle, most riveters were women. They had replaced men who'd gone to war. Women who'd never held a drill before 1941 now wielded pneumatic guns with precision and pride. They were called Rosies, a nickname borrowed from propaganda posters. But on the floor they were simply workers, tired, determined, and indispensable. Eleanor Watkins was one of them. Before the war, she'd been a seamstress. Her hands had stitched cloth, not steel. Yet that background gave her something rare, an instinct for patterns. Where others saw mechanical repetition, she saw flow. She noticed how each step affected the next, how alignment and timing could either speed up or slow down the entire rhythm of the task. That winter, production managers were under pressure from Washington. The bombing campaign over Europe had intensified, and every week, General Hap Arnold demanded more aircraft. Assembly rates had to increase, and every bottleneck was an enemy of victory. Boeing engineers held endless meetings on tooling and material logistics, but the real solution would come not from a boardroom, but from the factory floor. Eleanor's section was responsible for riveting the leading edge of the left wing. The process required coordination between two workers, one inside the wing, the bucker, and one outside, the gunner. They worked blind, feeling each other's rhythm through sound and vibration. Each rivet had to be perfectly flush. Too deep and the metal weakened. Too shallow and the airflow over the wing could be disrupted. It was meticulous, exhausting work. One day, after a series of delays caused by misaligned rivet holes, Eleanor asked her foreman why the sequence couldn't be reversed. Why they couldn't start from the inner spars outward, rather than the edges inward. The foreman shrugged it off. "We follow the spec sheet," he said. But Eleanor kept thinking about it. The next day during her shift, she quietly altered the order of her pattern. She began from the central spar, the backbone of the wing, and worked outward, letting the metal settle naturally into alignment as she went. The bucker, surprised, noticed fewer misfires. The rivets seated faster. The vibration through the aluminum changed. By the end of the shift, her section had finished its panel hours ahead of schedule. Supervisors noticed. At first they thought she'd skipped a step, but inspection revealed something astonishing. Her work was flawless.